Hello friends, welcome to CEC live lectures. Dear friends, today in this session we are going to continue further in our series on types of lasers. We have conducted 2 sessions on types of lasers where we discussed on the solid as well as gaseous lasers. In our previous session we discussed on the gaseous lasers, and we are going to continue further from the point where we left. Friends, for the discussion on the topic, we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is an assistant professor and she is teaching in YMCA Technical University. She is a prolific professor. Friends, if you wish to ask questions from Dr. Sonia Bansal on today's topic, then do call us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. You are requested to call in the last 10 minutes of the lecture only. Now, I would like to welcome our guest, Dr. Sonia Bansal, once again. Hello, ma'am. Pleasure to the lecture.
Dear student, we are discussing about the types of laser. First we discuss about the solid state laser, where we discuss about the different solid state laser. We are discussing about the various types of laser on the basis of active material which we are using. As we are talking about the solid state, where we use the solid as an active material, and then we discuss about the gas laser. In the last series we were discussing about the gas laser, where we discuss about the different gas laser. Helium neon laser, which is a helium neon is the active medium in the helium neon gas laser. Helium for the population inversion and neon for the lasing action. Similarly, we discuss about the CO2 laser, carbon dioxide laser, which is very important laser in many field of the daily life. Now we discuss about the next laser, which is the gas laser, and it is the excimer laser. What is the excimer laser? Excimer laser where we use the dimers as an excited level. Excimer laser constitute an interesting and important class of molecular lasers, where it first demonstrated in 1970, and it is a powerful ultraviolet laser. The active medium which we are using in the excimer is diatomic molecules that can be bounded into a single system when they are in the excited state only. Here we see from the diagram that this is the energy axis and this is the atomic distance between the R and H. Here we see that this is a one curve and this is the another curve. This is the excited level and this is the ground level. And here we see at the excited level there is a potential well. And this potential well, we are having the number of atoms at this well, and this is the excited state, and the molecule will jump from this excited state to the ground state. Why we are having the atoms at a excited state and the population state is the excited state? Molecules are not going from the ground state to the excited state, but its excited state is already populated because of the dimers. These diatomic molecules exist only as a monomers in a ground state. If we talk about these dimers, then these are diatomic molecules and they work as a monomer in the ground state. They repel one another in the atomic distances. Now, and excitation modify the state of atoms. There appears an attractive forces with other atoms. That's why they are on the excited state. Such molecules which exist only in the excited state are known as the excited state dimers, or we can call it as a excimers. That's why this is called as a excimer laser. Atoms of the inert gases can be bounded to molecules by imparting the energy to them. Now this is the excimer laser. Excimer state having the metastable state, which is the excited state. When the atoms are bound together in the excited state and can occupy the several vibrational levels in the potential well at the excited state. Here we define that this is a potential well, and this potential well having the various vibrational levels, and in this vibrational levels we are having the atoms, and these are filled according to the rule, and these are the populated state. These vibrations levels are filled. They excited by the passing a short intense electric discharge through a mixture of desired gas for the pumping. It means we are using the electric discharge for the pumping. Electrons in the discharge transfer energy to the lasing gas, causing the formation of excited molecules. Because of the discharge, we are getting the excited molecules at the excited level. Molecules remain excited for the 10 nanosecond. It means this is a metastable state, and molecules will be excited for this much time, means 10 nanosecond, and then drop to the ground state and dissociate. When they are going from excited state to the ground state, they form the lasing action. Where we have ULL, electron excited state, LLL, we are having the electronic ground state. Means atoms are moving from ULL to the lower LL, electronic ground state. Now PR, population inversion, occur as soon as the atom bound to form the molecules in the excited state. Means we excite the atom from lower state to the higher state, but here in the Excimer state we are having the bound state on the excited state of the atom. Once the molecules drop to the lower levels, then it separates out into the atoms, and lower laser level is also vacant. Again, when it go to the level, then it will go again to the excited state by forming the dimers. That's why it is called the excimers. Excimer lasers having the high gain, using no cavity mirrors are required in this type of laser. One fully reflective mirrors used in rear and unsilvered transparent windows used as a output mirror. In the previous lecture we have defined that we use two mirrors, one is partially reflected and another is fully reflected, but here in this Excimer laser we are having the one fully reflected mirror, and one fully reflected mirror is used and the unsilvered transparent window are used for the laser output. Fully reflected just to get the population of the molecules, and partially reflected, here we use the unsilvered transparent window for the output of the laser. And the example of active medium for the dimers are, what type of gases we use to get that Excimer laser, and we are having the excited rare gas dimers like argon, krypton and xenon, and these are the different wavelengths of different laser or Excimer laser. Here we are using the argon as a dimer, then its wavelength is 1260 angstrom. Argon chloride wavelength is 1750, argon fluoride 1930, krypton chlorine 2220, and so on. These are the different type of Excimers and which gives this type of wavelength. A rare gas oxide is also used for the lasing action, which is ARO, KRO and XEO. Means oxides are also used to make Excimers. A rare gas atoms in combination with the halides are also used, like ARF, KRF and XeCl. Now major application of this Excimer laser are mainly used in the refractive surgery on eyes and manufacturing of semiconductor devices. It is used in photolithography as a light source and used as a material processing, and this is the main importance of the Excimer laser with the pumping of the dye laser. As we know, for the dye laser, that is a liquid laser, we use the Excimer as a pumping source to excite the atom in the liquid laser. What are the chemical lasers? Chemical lasers is a part of the gas laser where we use the pumped by the energy liberated in the chemical reaction. These are that type of laser where we use the chemicals in as an active medium, and these chemical lasers are pumped by the energy liberated in the chemical reactions, and because of this we get the more atoms and molecules. And most known are HF, hydrogen fluoride, DF, deuterium fluoride. The hydrogen fluoride output wavelength is in the range of 2.6 to 3.3 micrometer, and deuterium fluoride's output wavelength is 3.5 to 4.2 micrometer. Then they operates on the vibrational transitions, as already we defined that all the gas laser work on the vibrational transitions of the ground state of the electronic. Then output wavelength always in the range of infrared region in the chemical lasers, and the primarily developed for the military and space application, where pumping power in the form of electric energy may not be available. Because of the chemical reaction, we can get the atoms and molecules pumped, and it produces the power of the several megawatt. And HF, hydrogen fluoride, whose wavelength is 2.6 to 3.3 micrometer, it is ingredient. Molecules hydrogen and fluoride gases, helium added as a buffer gas. And molecular species react at normal temperature under the external excitation such as UV reaction, and the reactions are highly exothermic, which produces a amount of chemical energy, and because of this chemical energy, the molecules and atoms will go to the excited state, and then we can get the population inversion from there, and we can get the lasing light. Next is XX energy is required in the pumping energy in the chemical lasers, enormous compared to the forms of the pumping energies. The reaction between the atomic and molecule H and F gases are like that: H plus H2, F plus H2, fluoride is added with the hydrogen, it will be HF excited state plus H, and this is the energy which is released, delta H is equal to minus 31.7, and H plus F2, which is HF plus F, and this much energy is released. This is a schematic diagram of a chemical laser. Here we see that the reaction produces the vibrationally excited HF molecules, and this will participate in the lasing action. All the reaction will takes place at the vibrational level, and at this vibrational level we can get the lasing action. End product contains the atoms of hydrogen and fluoride. Once reaction starts, is continue until all the molecule H2 and F2 are consumed, and it gives the laser output. Here this is a schematic diagram. We are having the different nozzles here. Then this is expansion nozzle. These are the brevister window. This is the output mirror, which is the rear, which is partially coated, and this mirror is the fully reflected mirror. From here we inject the chemicals in the laser, and this is the cavity in between, and brevister windows are used in the cavity. From here the gases are inserted like helium, and here this is a F2, and here hydrogen is injected into the cavity, and this is the heat exchanger which is used for the chemical reaction, and gas exhaust here, and from here the laser output will comes out. And the main application of this chemical laser is produce the high power weapons on the battlefield or in the space. Next, and the most important laser is the dye laser. Liquid laser, where we use the dye laser as a liquid laser. Liquid laser basically used for the tunable laser. Liquid laser, where we discuss about the one of the important laser, which is the tunable dye laser. As the name suggests, dye laser, it means the host medium is the dye, and dye in the form of liquid. How we get the liquid? We dissolve the dye into the solvent. Solvent may be of benzene, toluene, xylene, or any water, or you can also use as a solvent. Then active medium, a dye dissolved in a host medium of the liquid solvent. The solvent where that this dye can be dissolved. The situation similar to a solid state laser, where chromium neodymium and ions used in the solid host. And advantages of the liquid host is that concentration of the active ions can be easily varied. And this laser worked on the two states, triplet state and the singlet state. Typical dye concentration, we keep it as a 10 to power minus 4 to 10 to power minus 3 molar solution. And 10 to power 24 to 25 dye molecules per cubic meter is arranged. Most important dye which is used in the dye laser is the rhodamine 6G, and coumarin dyes is also used. And there are 200 dyes which are used in the liquid laser. The most important one is the rhodamine 6G. When used, produce the tunable output over the wavelength of the range 0.32 to 1.2 micrometer. We have a very broad range of the output in the liquid laser, which is from the 0.32 to 1.2 micrometer. And this operates both in the continuous wave and the pulse mode. And the pulse dye laser pumped by the flash lamp or other lasers. As we discussed here, that the excimer laser is used to pump the dye laser or the liquid laser. Here we can use the excimer laser for the pumping the molecules of the dyes. Then it must be of 400 joule in the 10 microsecond pulses. Continuous wave dye laser pumped by the CW lasers like argon ion, and output power must be of 2 watt. The gain dye medium is very high, and a small volume of dye solution is sufficient to sustain the lasing action. It means we can have the very low concentration dye for the lasing action. And organic dye molecules have the two sets of excited state. Here we see in the diagram we are having the two excited state. One is the singlet state, which is start from the S0. This is the ground state of the singlet state. This is the first excited state of the singlet state, and this is the second excited state of the singlet state. It means singlet state having the S0, S1 and S2. Another state which we are using in the organic dye molecules is the triplet state. One is T1 and another is T2. Here we see that these states having the different vibrational states, and molecules will excited from the lower state to the higher state. The transitions from the singlet state to the triplet state. This is the singular state and this is the triplet state, and these transitions are forbidden. But these triplet states are used to maintain the population in the dye laser. The pumping means population inversion takes place in the singlet state, and the emission is also, or the lasing action takes place also in the singlet state, but this triplet states required to maintain the population in these singlet states. But the transition from S1 to T1 is forbidden. The optical pumping excites the dye molecules from the lowest vibronic ground state S0 to the upper vibronic level of excited state X1. Here we see that the atoms are the molecules of dye excited from this level to this level, and from this level it will decay to the lower level of vibronic excited state S1. Here we see that the molecules excite from this A to this B. It means upper state of the ground state and the upper state of the excited singlet state. From this singlet state it will decay to the lower singlet excited state. From this excited state it will go to the lower ground state of the singlet state. Here we see that from here from here excited state to the lower excited state, it is a non-radiative transitions, and it excel ULL, undergo non-radiative transition to lower vibranic level of the L1. Here we are seeing that these molecules will drop to the lower level of the excited state. And then role of PLLL played by one of the upper vibranic level of the S node closely spaced level from the continuum. From here it will drop to the upper level of the lower ground state of singlet state. And here we are seeing that decay is taking place as excess of atoms are at this level. S1 will drop to the T1. From here T1 it will be absorption will takes place and the molecule will jump to the S2, and from here T2 there is a transition, there is a inter cross section and there is a collision, and here we use these molecules here to maintain the population at this level S1, and from S1 to S0 we are getting a laser transition. The laser transitions can be to various levels within a range defined by the vibrationally excited sublevel to the ground state. Here it means that we are saying the molecules jump from this level to the excited state, and from excited state it will jump to the lower level of the excited state, lower level of the S1. From this lower level of S1 excited state, the molecules jump to the upper level of the ground level. The molecule can jump at any vibrational level of the ground level, and because of that we can have the various transition in this case. That's why it is called as a tunable laser, and the laser operates over a wide or broad range of the wavelength, because the laser transition can be to various levels within the range defined by the vibrationally excited sublevel on the ground state. This is the schematic diagram of the dye laser. Here we see this is a qubit where the dye stream at a brevister angle is put, and this is the cavity and the mirror is used. This is the collimated mirror. This is the pump mirror. Pump the laser beam means we are using a laser source for the pumping the atom. The pump, from this pump the light will fall upon this qubit. From this qubit it will go to the collimated beam, and this is a cavity, and from this collimated beam here we are having the tuning element and the output mirror where we can get the tunable output of a laser. By this tuning element we can have the different wavelength of dye laser, and these are the different dyes and which are having this peaks. This is a variation tuning range. P-terephenyl is having the 3232 346, and the solvent is cyclohexane and 340, and pump source are here defined. There are different pump sources are used. Some we are Excimer, some flash lamps we use, and this is still been 420 where the peak wavelength are 424 to 449, and the tuning range is 410 to 470, and these are the different pump source. Argon UV, N2 is the nitrogen laser, argon and xenon chloride, and these are the solvent in which this stilbene dye can be dissolved. These are the ethanol, which we NH2O, which can be of the ratio of 9:1, methanol ethanol we can use, and sometimes H2O water can be used for dissolve the dyes, and ethyl glycol is also used as a dye in the dye laser. And here we are talking about the rhodamine G, and which is known as the rhodamine 590, whose range is from 548 to 633, and 560 to 610 we are having a prominent peak. And the source, pump source, for the different wavelength we are having the different pump source, and we are having the different solvent to get the output, different output. Sometimes we use the flash lamp, organ. If we talk in this range, then we use the organ. Flash lamp is also used, krypton. Blue green light is also used, and the arc laser is used in the rhodamine 6G, whose output is 560, and the solvent which we use methanol, ethanol, and ethyl glycol and H2O. These are the different solvents which use in the excimer lasers. Thank you.
With this note, thank you, and thank you so much for giving us this session. Friends, you are requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, we are talking on types of lasers, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor and she is teaching in YMCA Technical University. Friends, if you have any queries or if you want to raise some questions pertaining to the previous lectures on types of lasers also, then you can ask questions through our live session by becoming part, and for that you need to note down our number. Our number is 1800110430. I repeat, our number is 1800110430. All dear friends are requested to call in the last 10 minutes of the lecture only. Now I would like to welcome our guest Dr. Sonia Bansal once again.
Thank you. Dear student, we are discussing about the various gas laser. Up to now we have discussed the different gas lasers, and now we will discuss about the homojunction, heterojunction laser, which are very important laser, and this comes under the semiconductors laser. Now we in this part we will discuss about the what is the homojunction laser, what is the heterojunction laser, we define the principles of heterojunction laser, then we define the geometry of the laser diodes, and then we define the quantum well lasers. Now, what are the two basic conditions for designing the laser are required? One is the optical gain. Optical gain based upon the medium which we are using, medium which possess the desired energy level structure to support laser action. In the case of diode laser, there will be the active region of the PN junction. PN junction is the active region in the diode laser. To establish the population inversion in the laser system, the forward biased current supply to the diode laser, which are important in the when we define the semiconductor lasers. Then second most important condition is the feedback. What is the feedback? Homojunction layer, that one end cleaved and the other roughened. This is achieve the optical feedback. Optical gain of the laser system can be achieved by this manner. Such system is often termed as a Fabry-Perot cavity. Now we discuss about the threshold current density. Here we consider the diagram which is showing the active region. This is the active region in between the PN junction and mode volume of the semiconducting laser. Here we can get the output in this active region. This is the mode volume which is having the thickness D. As we recall from then when we are talking about the forward biasing, then EV, electron volt, is greater than equal to EG. EG is the band energy, band gap of the material. The electrons from the degenerated dropped to the N, and holes from the degenerately doped P. Here we see that the electrons from degenerated doped N and holes from degenerately doped N. We can get the electrons and holes by doping. That's why we are having a PN junction will be injected across the junction to create the population inversion. Here we achieve the population inversion in between the PN junction by doping the PNN respectively. The population inversion is created in a region called the active region, as we are getting the population in the form of PNN in this active region. The radiative transitions may occur resulting in stimulated emission when the photon is absorbed by the electrons in the conduction band, and then we can get the population inversion. The radiation generated will be spread out in the vicinity of the active region and is almost confined in the thin layer shown above as the mode volume. This active region is thin, and from this thin region the radiation can be generated, and this will produce the laser output. Here we are using the PN junction, and this is also work as a depletion layer. Then in this depletion layer the holes and pairs are generated, and holes and pair generated when the electric current pass in the N and P junction, then this will comes out in the form of energy, and this will come out in the form of the light. Now we see the schematic diagram of the homojunction GaAs, gallium arsenide diode laser. Here we see this is a P plus gallium arsenide, and this is N plus gallium arsenide. This type is roughened, and the upper part is the cleaved, and the metal contact, here we are having the plus for the P and negative for the metal contact for the negative, and minus for the electrons. Cleaved end 110, natural cluster planes of the junction, so the end of the we can get the output of the laser. That part is the roughened, as we already discussed that this is used for the cavity, and we can say this is a form of the cavity. The laser beam will be comes out from this cleaved end, and the junction active region is in between the P type and N type gallium arsenide, and where we are having the two contact, metal contact at the upper level and at the lower level, to the electrons and molecules can be charged. The carriers in the active region increases the refractive index of the gallium arsenide. The refractive index increment is only 0.02. It is very small, hence it is not a good dielectric waveguide. The beam therefore can be spread out to the surrounding regions, that is in the form of mode volume. Here we are see this beam will be spread up around. The vigorous pumping is therefore needed to enhance the lasing. If we increase the lasing action, then we can get the if we increase the pumping and if we increase the population inversion, then we can get the good output. The threshold current for the pumping action exceeds approximately 400 ampere milli minus 2. The threshold current density, where we define as if the injected carrier concentrations become large enough. If the injected carrier concentration become large enough means we are adding the N and P type of NNP type of doping in the material. The stimulated emission can exceed absorption, so optical gain can be achieved in the active region only. With the appropriate configuration to achieve the optical feedback, these are the most important terms in the semiconductor laser. With the appropriate configuration to achieve the optical feedback, the laser oscillations occur when the gain exceeds the losses. When the gain is more, then we can get the laser output. For significant gain, a high current density is necessary. Because of high current density, we achieve by doping the NNP type of atoms. The onset of the lasing is characterized by the specific injection current known as the threshold current. Threshold current to maintain the pumping in the semiconductor laser. Since the simple homojunction laser has a very high threshold current and it is considered not efficient. The onset laser action at the threshold current density is indicated by the increase in the radiance of the emitted region. As the lasing, if we want to increase the lasing action or we want to increase the radiance of the emitted region, the threshold current density injected must be increased. If the threshold current density is increased, then we can get the good laser output, leading to the marked decrease in the spectral width. The broadening of the light will be less. This is the threshold. This is the output of the threshold current density. This is the typical output spectrum where we are having the stimulated emission. This reason define the stimulated emission and spontaneous emission. The output power. This side is the output power and this side we are having the current density. If we take the graph between them, the current density will be increases, the output power will increases. Here in the case of spontaneous emission, the optical power versus wavelength, we are having the broad band. But here in case of the laser, the output power and the wavelength versus, we are having a sharp peak. This sharp peak is only because of the stimulated emission. Now this is the difference between the LED and the laser. LED having a broad band and laser having the sharp peak. In conclusion, for the homojunction laser, we can define the main problem with the homojunction laser diode is that the threshold current Jth is too high for the practical application. To get the laser light, this we are having the we will get the current density should be high, but at a particular value, that means threshold current density is used for a particular applications. The Jth increase with the temperature means the current density, threshold current density will increase with the temperature too high at the room temperature, not continuous, but the pulse laser output will be formed. The homojunction lasers has poor optical, less carrier confinement. That's why it is having the drawback. If the Jth is low, if the Jth increases the temperature, that these two causes will be takes place. If the Jth is low, improve rate of the stimulated emission and improve efficiency of the optical cavity. It means here in the diagram, the value of J, this is the threshold value of the current density. About it, we are not able to get the good laser beam. But at this value, in jth value should be low, we can get the good stimulated emission and the improved efficiency of the optical cavity we will achieve. To get low jth, what we should do? Confined carriers in a narrow region. This region should be narrow and the molecules will be confined in this region. And the carrier confinement, the build dielectric waveguide around the optical gain region increase photon concentration, hence stimulated emission will takes place. The two confinement is very important to get the low current density. One is the carrier confinement and second is the photon confinement. How we achieve this? We achieve this by adding some impurity that is in the form of heterostructure laser diode. What is the heterojunction laser? It will be single and the double. Here we are having the two example. We are having the two metal contact. This is one type of the semiconductor laser. This is N gallium. This is N gallium aluminum arsenide. Here gallium arsenide is sandwiched between the higher band gaps. One is gallium arsenide. This is gallium aluminum arsenide and this is gallium aluminum arsenide. This is N type and P type. This P type gallium arsenide is sandwiched between these two band gaps, higher band gaps elements, and this is defined here for the single heterojunction laser because we are using a single layer of the gallium arsenide, that is the P type, and the size of this layer is 1 micrometer. You know that it should be very small, that's why its size is 1 micrometer. And here we are having the metal contact on both the side, and this is the this is the positive side and this is the negative. Here what type of heterojunction laser we are having? N, P and P. Here this is the NPP heterojunction and this is a single heterojunction laser. And gallium arsenide sandwich between the higher band aluminum gallium arsenide, and gallium arsenide is act as an active medium in the heterojunction single laser. Here we see this is the heterojunction laser which is using the double layer. Here this is a N gallium arsenide, this is the P gallium arsenide. These are the two active medium to achieve the population inversion and to get the output. Now this type of laser is the NNPP laser. This is the heterojunction laser having the double layer of the one is N type and one is the P type. Again we are having the different metal contact at the two ends. Now this is known as NNPP type of heterojunction laser. This is the diagram. Here how it is work. Here we see that a double heterostructure diode has the two junctions which are between the two different band gaps semiconductors. One is gallium arsenide is in between the aluminum gallium arsenide and aluminum gallium arsenide. This is for the case of the homojunction. And here we see that that simplified energy diagram under the large forward biasing. The laser combination takes place in the gallium arsenide region. Here this band gap is less, and in this region the laser recombination takes place in the P type of gallium arsenide laser. This is a P type gallium arsenide laser, and this work as in the active layer. Now higher band gap material have a lower refractive index, and this region is having a larger refractive index. Here we see that the band gap of active medium is less as compared to the two junctions which are added in the gallium arsenide, and we are getting the laser output in the gallium arsenide. Gallium arsenide, as because its a refractive index is less as compared to the two materials, two junctions are added in it, and the photon density in this region is more as compared to the other region. Aluminium gallium arsenide layer provide the lateral optical confinement. In this region we can get the laser output. The carriers and the photon confinement, here we see in this diagram, this is the ray picture of the helium neon laser. The thickness of this active medium is 2D. Here we are seeing that how it is moving from N to D. Here we are having the different active layers in between the N and P type of semiconductors. Then we are having gallium arsenide and aluminum arsenide. One is have the different refractive index, means refractive index of gallium aluminum arsenide is less as compared to the refractive index of gallium arsenide. That's why we are getting the good laser output. And here we see that and band gap is also different. The band gap of gallium aluminum arsenide is more as compared to the band gap of gallium arsenide. If we define any heterojunction, homojunctions laser, then these two conditions are must. The refractive index of the active medium, active layer must be high. The band gap of the active medium must be low. The band gap difference forms the barriers for a E and H electrons and hole to diffuse between the gallium arsenide to sandwich the layer of the gallium aluminum arsenide, where we are having the carrier confinement in the gallium arsenide. The step different in the refractive index, where we are having the photon confinement or we are having the optical confinement. Energy band gap, gallium aluminum arsenide is greater than that of the gallium arsenide. Photons produced a gallium arsenide will not be absorbed in the gallium aluminum arsenide because of the larger band gaps. Photons cannot be absorbed in the gallium aluminum arsenide. It is only absorbed in the gallium arsenide. That's why it is in the active medium and we are getting the output. The strip geometry of the double heterojunction laser, which is having the features of the oxide laser or the high resistance laser, which produces by the proton bombardment between the metal contact and the semiconductor. Because of the proton bombardment, we are having the two layers. The restrict current along the junctions into a narrow strip, which is having the few microns. Small jth means current density with the high power. Continuous operation will be takes place. Used largely in the optical fiber communication. This type of laser are used in the optical fiber communication. The configuration is shown here. We defined already of the gallium arsenide and the gallium aluminum arsenide. This is a schematic diagram of double heterojunction StrpeLaser diode. This here we are having, this is the elliptical laser beam which comes out between the P gallium arsenide active layer. Here already defined, this is a P N type of heterojunction laser. First layer is of the oxide insulator. Here we are having the strip electrode whose width is W and length is L. After that, a layer of oxide insulators and then P type of gallium arsenide contacting layer is attached here. P type of aluminum gallium arsenide, which is confining layer, and after this layer P type of gallium arsenide active layer is doped in this system. Then N type of aluminum gallium arsenide, this P is in between the P and N type of aluminum gallium arsenide, which is a confining laser layer. Then again the N type of gallium arsenide substrates are used here, and this is work as a substrate. And lastly, one electrode is again coated in this system. Then the active region, where the J must be greater than, current density of the active region must be greater than the current density threshold value, must be greater than the threshold value, and that is the emission region, where the output of the laser light can be get. This is a schematic illustration of the structure of the double heterojunction stripped contact laser light. The material criterion selection for this type of laser: to date, gallium arsenide and gallium aluminum arsenide are largely used to prepare this type of laser. Advantages of gallium arsenide and gallium arsenide system is that it is having a direct, gallium arsenide is a direct band gap material, and gallium aluminum arsenide is the direct, having the direct when X is less than 0.45. The lattice match between the gallium aluminum arsenide and the gallium arsenide is very small, which is 0.1%. Therefore, the EPI growth can be achieved. The band gaps of both the materials can be manipulated to produce the SH or DH single heterojunctions or double heterojunctions laser for the high optical and carrier confinement. For the optical fiber communication, the wavelength of this type of laser is in between the 1.1 to 1.6 micrometer, and they are mostly used for the optical fibers. This is a typical question we can take it here on the gallium arsenide and gallium aluminum arsenide. Then this is a EG X for the 1.24 plus 1.24 X electron volt empirical relation. Calculate the band gap of aluminum arsenide is to be used as emitter for the optical fibers communication at the wavelength of 1.4 micrometer. This is the diagram which defines the band gap for the different heterojunction or homojunction lasers, and this system can define the lattice constant as well as energy gap between the different materials which are using to define the heterojunction or homojunctions lasers. Now, what is a quantum well laser? Quantum well laser is a structures having the similar as the double heterojunctions laser, except that the thickness of active layer is very small, which is in the form of nano, sometimes is called as a nano laser. The active layers is in between the 10 to 20 nanometer. It is very small as compared to the double heterojunction, and the narrow band gap gallium arsenide sandwich between the larger band gap gallium aluminum arsenide. With this configuration, density of state near the bottom of the conduction band and the top of the valence band increases. It means the current density is more significantly, and hence the population inversion can be achieved because of the increase of the current density. Better population inversion, smaller active layer, and hence the Jth is smaller. But in a single quantum well, extremely narrowness to the active region created the poor optical confinement. Output will be less. Then for this, the multi-quantum well structures are used. The single quantum well can be coupled to produce the multiple quantum well structures. Overall active region is now thicker in case of the multiple quantum well. It means from the single quantum well we can achieve the multiple quantum well, and the overall active region will be bigger in this case. The carrier which are not captured in the one well can be captured by the second well, so that we can get the good output. The multiple quantum well has a higher current density than that of the single quantum well, as a single quantum well having the 1 milliampere, but the more optical power due to the better optical confinement. So So in the quantum well, multiple quantum well are important in case of the the quantum well laser as compared to the single quantum well, and these are also used in the optical fibers. Thank you.
Thank you, ma'am. Thank you so much for giving us this session on types of lasers. Dear friends, if you have any question or if you want to give your feedback for this lecture or the lectures we have conducted on types of laser in the past, then you can write to us at info.cec@nic.in. Your feedbacks and questions are welcome. Today we are taking your leave with the promise that we are going to meet again soon and would be discussing more. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.